So now we will see how the load would be shared by the two transformers which are connected in parallel. Okay, for that what I will do is I will just try to draw a simplified circuit of the secondary side of these two transformers. Okay, so what we can see is, let's say, so this is impedance ZEA, this is EA voltage, and this is EB voltage, and this is ZEB voltage, and obviously they are connected at a common point, and then this is feeding the load. So you can see here, this is the common point, right, which is where the load is also connected. So let's say if I mark it point by point O, so this O is actually connected with these common points, right? So you can think of that this is connected here. Okay, and since we said that EA, the voltage, we have already seen that this voltage EA minus IC ZEA is equal to EB plus IC ZEB. That means this terminal voltage is same, right? Okay, and since the turn ratios are same, that means EA is equal to EB. If the turn ratios are same here, you can see here, if the turn ratios are same, whatever voltage is applied here, depending upon equal turn ratio, same voltage will appear here as well, right? So what we can say is EA is equal to EB. So if we further simplify it, it would be so this is EA is equal to EB, okay, and this is your voltage V here. Okay, I think I have shown it by V. So this is V here, and this is ZEA, and this is ZEB. So current flowing in the transformer ZEA from the series impedance of transformer EA, let's say that is IA here, and current flowing in the transformer B winding is IB here. So this is IA and this is IB. So the demand of the load current IL would be shared by transformer A and transformer B. So what you can see here is, we can directly say that this impedance drop here and this impedance drop here, they are same, right? They are connected in parallel, right? So we can say that IA ZEA is equal to IB ZEB, and also you can see that this IA plus IB would be equal to IL. Okay, so what would be IA here? So let's say I'm just replacing IB by this relation. So this IA plus IB would be IA ZEA upon ZEB is equal to IL, and then further we can see that this would be equal to IA ZEA plus ZEB upon ZEB. So this IA is equal to ZEB into IL upon ZEA plus ZEB. And what about IB? If you see IB, this would be ZEA upon ZEA plus ZEB into IL. Okay, so multiplying, let's say multiplying by these expression, by, let's say, V conjugate. That means it is the apparent power of the transformer A, and V conjugate here, that is the apparent power of the transformer B. And if I multiply it here by V conjugate and V conjugate here, so what we can say is this SA is equal to ZEB upon ZEA plus ZEB times SL. Okay, SL is the apparent power of the load, and similarly this is a small a, and this is SB would be ZEA upon ZEA plus ZEB into SL. Okay, so what about the SA upon SB? If you see this ratio, that will come out to be ZEB upon ZEA. SA into ZEA is equal to SB into ZEB. So if this leakage impedance of both the transformers, they are equal. If they are equal, then obviously the transformer, if this ZEA and ZEB are equal, then this transformer, these two transformers will share the power of the load equally. Okay, but let's say if this impedance of transformer 1 ZEA is smaller than ZEB, then what will happen? Then you can see that this transformer A will take more apparent power than B, because this product has to be same. So if ZEA is smaller than ZEB, that means SA would be greater than SB. So SA will take more apparent power of the load than, that means transformer A will take more apparent power of the load than transformer B. Okay, so let's say these two transformers you are using, and gradually you are increasing the load. Okay, so you will observe that transformer A will get loaded first. If your the leakage impedance of that transformer A is smaller than the transformer B. If you try to write these impedance in per unit, then what you will see that, let's try to write in per unit system. So if I divide this equation by V squared, so SA ZEA upon V squared is equal to SB ZEB upon V squared. V squared is what? V squared is this voltage here, right? So what is this expression? V squared by SA, that is the per unit. If you want to write the Z base of transformer A, that would be V square upon SA, and Z base of transformer B, if you want to write, that would be V square upon SB, right? And so this is actually equal to Z base A. So Z actual upon Z base A would be what? That would be per unit of transformer A in its own base. In its own base means you have chosen different power there, right? We have said that if you talk about the per unit impedance of two transformer, then that means they had been defined in their own base, in their own apparent power, and in their own rated voltage. So Z per unit A of transformer A, or the better way would be writing Z A per unit would be equal to ZB per unit. Okay, so what does that mean? That means if we want that the transformer shares the load as per their rating, then they should have equal per unit impedance, or the ratio of their apparent power rating should be inverse of the ratio of their leakage impedance. Okay, you just think of, let's say, the transformer SA or the transformer A, it is having a higher impedance. Okay, consider an example. So now consider a case, consider an example where there are two transformers. Transformer A, whose apparent power rating is, let's say, 60 kVA, and its equivalent impedance is, let's say, 40 ohms. And there is another transformer, transformer B, whose apparent power rating is 40 kVA and its leakage impedance EB is 60 ohms. And let's say the load power is 100 kVA. Okay, so I have not mentioned the power factor here. So how much apparent power or how much load will this transformer A will carry? So let's say SA will carry ZEB upon ZEA plus ZEB into SL, and ZEB is 60 upon 100 into 100 kVA, which is 60 kVA, and this is the rating of the transformer as well, so it will carry that much power. And what about SB? And if you'll see that SB, the apparent power which the transformer B can carry or which can handle, that would be 40 kVA. Now just think of reverse, like this transformer, this leakage impedance ratio is not the one which is given here. Okay, so if you see, if you see in that case, let's say this is case 1, let's say case 2, transformer A is having 60 kVA and load impedance, the leakage impedance ZEA is also 60 ohms, and transformer B is having 40 kVA, that rated power there, and ZEB is 40 ohms. Okay, so now you calculate SA. So this SA would be ZEB upon ZEA plus ZEB into SL, and it will come out to be 40, because ZEB this time has been given 40 ohms, so 40 upon 100 into SL, which is 100, so this will be 40 kVA. So there is no problem for transformer A, but see for transformer B. So this transformer B would like to carry 60 upon 100, because this is equal to ZEA. Now this ZEA has been given 60 ohms here, okay, into SL, which is 100 kVA, and this is 60 kVA. Now is this a desirable thing? The answer is no. The reason is, you see here, because this transformer B has been designed for 40 kVA only. Okay. So this transformer B won't be able to cater a 60 kVA of load. Okay. So the thing is, the impedances here and the apparent power rating, they should be inversely proportional to each other. The ratio of apparent power rating of the transformer and the leakage impedance, they should be inversely proportional. Okay. So what we have seen that the transformer which is having a lower impedance, that transformer will get loaded first, right? So the maximum loading which, or the maximum load which these two transformer can carry, that will depend upon the transformer which is having the lower impedance. Okay. So I would say the maximum loading, because that would be the condition when both of the transformer would be under rated condition and none of the transformer would be in the overloading condition. So if we want that none of the transformer is overloaded, then we have to ensure the rating, we have to ensure that the load must not exceed the following expression. Let's say here the ZEB is smaller than ZEA. So in this condition, transformer B will actually decide what would be the rating of the load, the maximum load. So I would say SL max would be given by S2 rated into ZEA plus ZEB upon, and we have seen here, right, for SB we used to take the impedance of the other transformer, right? This is ZEA, and in this condition if you see, so S2 rated was 40 kVA into ZEA plus ZEB is 100 upon ZEA is 60. Okay. So this will come out to be, okay, so the SL max would be 66.66 kVA. And let's say if ZEA is smaller than ZEB, then SL max would have been S1 rated into ZEA plus ZEB upon ZEB. This is the condition when these two transformer is not having the ratio of the kVA rating as the inverse of the ratio of their leakage impedance. Okay. Or in other terms, if these two transformers does not have the same per unit leakage impedances, then in that case we have to see which transformer will get loaded first. Okay. So let's say in this case, when we have calculated 66 kVA should be the maximum load which these two transformer can actually cater. So just try to find what would be the load distribution now for transformer A and for transformer B. So obviously for transformer A, it would be ZEB upon ZEA plus ZEB into SL, right? And here ZEB is 40 upon 100 into SL, which is 66.66. Even the 40% of this, right? And this will come out to be, so this will come out to be 26.66 kVA. And what about SB? That would be ZEA upon ZEA plus ZEB into SL, So ZEA is 60 upon 100 into 400 by 6. So that is 40 kVA. Okay. So now you see here. So transformer B has reached to its maximum capacity, 40 kVA. So the transformer which is having a lower leakage impedance, that transformer will reach to its maximum or will reach to its rated apparent power. Okay. And the transformer which is having a higher leakage impedance, and if its apparent power rating is also higher, then it won't be utilized fully. So we need to ensure that this ratio is actually maintained. This ratio should be maintained to utilize the transformer fully. If we are near to this ratio, the power sharing would be the transformer would be loaded optimally. So in this parallel operation of transformer, we have seen that we said that these conditions should be met. One, it should be properly connected as per their proper polarity. Okay, and they should have the equal voltage ratio, and it will avoid the zero circulating current. Okay, and I said the per unit leakage impedance of each transformer should be equal. Okay, or the ratio of the kVA rating of the transformers should be inversely proportional to their leakage impedance. Okay, and the fourth condition, so I will just discuss briefly about it. See, the leakage reactance and winding resistance, it actually decides the power factor angle at the primary side. Okay, or overall power factor of the transformer. Okay, for an ideal transformer, whatever is the load power factor, same will appear at the primary side. But we have seen in a practical transformer that the power factor angle of the primary side, which a primary observes, would be different than what is actually there in the load power factor angle. So if this ratio is not maintained, then actually the real power sharing between these two transformers won't be equal. So we have to ensure that the apparent power rating of the transformer, the ratio of the apparent power rating of the transformer should be inversely proportional to the actual impedance, leakage impedance of the transformer in magnitude, and the angles of these two leakage impedances, they should also be same. Then this power factor, then the transformer will actually share the equal real power among themselves. Okay, so with this we will stop here.